In this video on systems of equations, we're going to be looking at our third and final non-solution system. This is when our three planes take the form of a triangular prism, which is a three-dimensional solid with a triangle on its face, like this. It's then extended in 3 dimensions to form a prism. Of course, because our three planes do not meet at a point or along a line, this will be a non-solution system. It's important to note that here, and here, 2 planes at a time are intersecting along a line, creating infinitely many solutions. But those infinite solutions only work for 2 planes and not for all 3. So it does look like an infinite solution system, but it's not. It is a non-solution system. The examples numbers has been changed in order to reflect the system, so let's put them in our solver. Okay, now we're going to go ahead and solve. And we can see that our solutions are decimal values, which is a little bit different to previous examples. And this just happens to be based on the numbers. It's important to note that you can have decimal or fractional solutions to your problem, and it doesn't make them any less valid. Of course, we're still getting this error message here, so we know that it's either infinite or no solutions. So it's important to either visualize it geometrically or to look at the equations in a bit more detail to see if we can find any patterns. What we could do if we wanted to is plug in these solutions like we did in our previous video and see which equations each solution worked for. But as we already know the result of that, it will work for 2, but not 3. We're going to leave that for this video. It's a little bit harder to see in this image, but in GeoGebra, we've graphed our 3 planes, and we can see that it does form a triangular prism, but it is a little bit difficult to see. The faces of our triangle will be here, and the corners are extended here to make the prism. One important distinction of this geometric design here is that this line here, for example, runs parallel to the blue plane. It's the plane opposite it. And so even if we extended that line and we extended that plane to infinity in 3 dimensions, they still will never meet because they're parallel, meaning that we're never going to get that third plane matching up and getting a full solution here. Same thing with this line here. It runs parallel to the opposite, which is the green plane, and so they will never meet and we won't get that solution. And with the last one over here, that runs parallel to the red plane. How do we recognize this inconsistent system? By looking at our equations here, you might recognize that we could add these 2 together to almost match up with the third equation. We can see that the x coefficients do match up, so do the y, so do the z, but not the constant term. If they did match up, it would be an infinite solution system, which we saw in an earlier video, where the coefficients and the constants match up perfectly. However, because this is not 7, where there would be a perfect infinite solution, because it's 10, it means that it's been shifted outwards. So you can imagine that, say, this red plane over here has had a shift. So if you imagine in the image that I'm drawing now, that's what the plane could have looked like. And that's where it would have intersected with the blue and green plane and created infinitely many solutions. However, when that 7 was shifted to 10, it shifted it out and created no solutions and this triangular prism shape. It's also important to remember that any of these equations could be multiplied by a number, say 2, 3, or 4, or even negatives. So you need to make sure that you are checking for any multiples there in order to add them up and get your system. So just remember that the coefficients should add up and be perfect. However, the constant term will be different in order to create this kind of system. It's really similar to the infinite solution system. It has a different constant, and that's why we have no solutions. And that's it. Thanks for watching.